In this video, I'm going to solve exercise 3, page 92. Consider the points A, B, C, D, and E. So you can plot any 5 points without any condition, A, B, C, D, and E. The first question is, part A, construct the point M so that AM equals 2AB plus BC plus DE plus BD. So to construct this point, first we will try to simplify this long expression here. Notice, for example, that here this vector ends with B and this one starts with B. So we think of trying to combine them using Chase's relation. However, we have a problem here. Here we have 2AB and here we just have 1BC. So we cannot combine them directly. What we can do is we can split this vector. We know that 2AB is AB plus AB. So I can write it as AB plus AB. And I'll copy the remaining vectors. So BC plus DE plus BD. Now we can try to apply Chase's relation. So first notice, as we said, AB plus BC, using Chase's relation, this will give the vector AC. And notice also that vector AB plus BD, the resultant vector will be vector AD, since the ending point here is the same as the starting point here. So this will give vector AD. And I will just add DE. Notice again that the ending point of this vector is the same as the starting point here. So I can combine them again. So I can combine this with this to get AD plus DE, which is AE. So we have AE plus AC. Now we can't simplify any further, but we notice that the two vectors start from the same point. So to construct their sum, it's enough to complete the parallelogram. So I'll just draw a quick sketch here and then go back to the original figure. So let's say this is AE and this is AC. We know that AE plus AC, since they start from the same vector, should be A something. So A here, it's AM, where M is the fourth vertex of the parallelogram ACME, or EACM. Okay, so this is just a sketch, but it's not the original, it's not the answer. Okay, so this is a sketch. On Scratch you do this. Okay, so we notice since AM is equal to AE plus AC, this means that M is the fourth vertex of the parallelogram EACM. So I'll write it here. So M is the fourth vertex of the parallelogram, or PARM, same meaning, EACM. Now let's go back to the real figure in GeoGebra. So we said here, I want AM to be AE plus AC. So I will draw first vector AE and then vector AC and then complete the parallelogram. So let's start with vector AE. This is vector AE and this is vector AC. Now I want to complete the parallelogram. How do we complete the figure to get a parallelogram? For example, one way is to start from C and draw a vector which has the same direction as vector AE, okay, and same sense and same magnitude. Okay, so I will complete this. So draw point M such that CM equal AE to get the fourth vertex of the parallelogram. So how can we do this easily? Notice here, to move from A to E, so to move from A to E, I move 2 units downwards, then 1, 2, 3, 4, 5. 5 units to the right. So from A to E, I move 2 down, 5 to the right. So from C to M, I should also move 2 down and 5 to the right. So move 1, 2, then 1, 2, 3, 4, 5. And here we should have the fourth vertex of the parallelogram. Okay, so this is the fourth vertex of the parallelogram. So we get this parallelogram, and vector AM is this. So AC plus AE is AM, where M is the fourth vertex of the parallelogram. Now let's move to the second part. We have AN given, and we also want to construct point N. So let's simplify. First, let's try to flip all the minuses to pluses. So we have here 1 minus, so this becomes AB plus AC plus CB. Can we combine vectors using Chase's relation? The answer is yes, because we have here AC and CB. So AC plus CB will give AB. So now we have AB plus AB, which is simply 2AB. So I'll draw here a quick sketch. So let's say we have a vector AB. The vector 2AB, so how do we draw 2AB? 2AB is the vector that has the same direction, because 2 is positive, same sense, sorry, because 2 is positive, same direction, and double the magnitude. Again, so AN equals 2AB. Since 2 is positive, so in addition to having the same direction, the two vectors have the same sense. So same direction, same sense, but the magnitude of AN is double that of AB. So I will extend AB in the same sense. Okay. So notice here B will the point B will be the midpoint of AN. AN. So this is N. Okay, so AN is double AB and in the same sense. So now let's draw it on the real figure. So I will draw vector AB. Okay, and then I will extend it in such a way, extend the line A or segment AB in such a way that B becomes the midpoint of this. We can think of this in another way. I can say to move from A to B, I'm moving 1 unit to the right and 2 up. So to move from B to N, I should also move 1 unit to the right, 2 units up. So here we will have point N. So this is vector AN. Okay, so AN is equal to 2AB. Now we will move to the next part. Part C. We have AS equal to this, and we want to draw or construct S. So first let's try to simplify also. I will flip the minus to a plus, so this becomes plus CA plus AD. Okay. Notice I can combine CA with AB or with AD. It doesn't matter because the ending here is the same as the starting here, similarly with AB. So I will combine them to get, so these two will give me CD. Now notice here I cannot simplify any further, and A and C are different points, so the two vectors AB and CD do not start from the same origin. If they start from the same origin, I can use the parallelogram rule. If the ending point is the starting point of the second, I can use the sum of two consecutive vectors, or Chase's relation. So what can we do in this case? We can create a point. So I can create a point, let's say F, so AB plus BF, okay, such that BF vector is equal to CD vector. Okay, so I'm doing this because I want the ending of the first to be the starting of the second. I could have chosen another vector, let's say AF or AK, let's say, okay, such that the first point, the origin here is the same as the origin here. Why? Because if I do this, then I can use the parallelogram rule to get S. And if I do this, I can use Chasel's relation. So either one is correct. I will use Chasel's relation in order not to draw more parallelograms. Okay, so I can, when I write here BF, I have to define what F is, because F is not a point in the given. So I have to say where F is the point defined by BF equal CD. Okay, so let's go to the figure and let's start first by drawing F. So how can we draw F? BF, we said BF equals CD. So I will draw first vector CD. So this is CD. And BF should be equal to CD. So to move from C to D, I move 3 units downwards and 1, 2 to the right. So 3 down and 2 to the right. So to draw BF, vector BF, I also have to move 3 units down and 2 to the right, because BF is equal to CD. So I start from B, move 1, 2, 3 units down, then 2 to the right. So I will get this point here. So this point will be F. Okay? And this is vector BF. So notice CD equals BF, parallel, so same direction, same sense, and same magnitude. Now, going back to the question, we have AB plus BF is AS. So notice this is equal to AF. Okay? So AS is equal to AF. Since AS is equal to AF and A is the same point here, then S and F are confounded. They're at the same point. So S and F are confounded. So I will just plot point S above. So this is AF vector, and S I will just plot it above F, on F. So S and F are confounded. Or I will write S is confounded with F, it's the same. So this is just to explain our construction, how we did it. Now the last part is not construction, so we're done with construction. We want to show that Sn is equal to AC plus dB. So this is the question, to show this. Okay? So what do we know? So we go back to our given. We know An and we know As. So from the previous given in part B, they gave us An. You can go back here. So An is given this to be this vector. And in part C, we are given As. Okay, so I have An, given An and As. So this is from part A and from part B, and this is from part C, and we want to find Sn as to prove that it's equal to this. So how do I find Sn knowing An and As? So clearly, since we know An and As, we think of inserting here letter A and apply Chasel's relation. So this will be Sa plus An using Chasel's relation, or Chasel's rule. Then we know that Sa is minus As, so this becomes minus As plus An. Now we can use any form we want for As, the one that we concluded after simplification or the original one. I will use the original one, but it doesn't matter. So As was AB minus AC plus AD. Okay, this one. So I will multiply by minus, so we get minus AB plus AC minus AD. And An, if you go back to the previous part, part B, is AB plus AC minus BC. Now we try to simplify. Notice here we have AB and minus AB, so they cancel out. And we have AC plus AC, which is simply 2AC. I'll change every minus to a plus, so this is minus, so this becomes minus DA, plus DA, sorry. And minus BC becomes plus CB. But this is not what we want. Our goal is to show that SN is equal to AC plus DB. Okay, notice here I have 2 AC, not 1 AC. So to get rid of this to one of the ACs, I should have here some CA. Okay, to do this, I can do this in different ways. So for example, I have C here, I can insert A if I want here. So I get CA. Okay, so if we insert here A, we get CA. So it would cancel out, so which is minus AC, so it would cancel out one of the ACs here, so we get what we want concerning AC. And also I want to have D with B, not with A. So I want to have D with B, so I can insert here letter B, so I get DB, and we see how this works out. Okay, so by doing this we are applying, of course, Chase's relation or Chase's rule. So at this step I will apply Chase's rule. So this becomes 2AC plus, so DA is DB plus BA by Chase's rule, and CB is CA plus AB. So again, 2AC plus CA is 1AC, but I will write it in detail so that it's clear. So this is plus DB. BA and AB gives a 0 because it would give BA plus AB is BB, which is the 0 vector. So I will write it here if you want. We can simply cancel them out. So this is BA plus AB gives this vector, which is 0. And I will flip CA to get minus AC. Now, 2AC minus AC is simply AC plus DB plus BB, which is the 0 vector. So this is equal to AC plus DB, which is what we want.